Hello friends, welcome to this video about the implementation of the restoring division circuit. The objective of this video is to explain how to implement the circuit for the restoring division of binary numbers. In the previous video, we explained the process of the restoring binary division method as an introduction to the present video. So, after the process, we are now going to see how to implement it. If you haven't seen the previous video about the process, I recommend you to check it first. What is the restoring division algorithm? The restoring division algorithm is a method for performing binary division where partial reminders are restored to their original values when they become negative during the process. It is suitable for hardware implementation because through successive iterations it helps to simplify the circuit hardware for the binary division. The restoring method is focused in solving the tricky story of finding out if the divisor goes or if it doesn't go. We, as people, we are able to do so in the division through a try and error method, but the machines cannot do that. So, from the machine perspective, the computer goes through calculating all intermediate reminders, doing a trial subtraction, and restoring them back to their original values when they become negative. This process is shown in the following diagram. This flow diagram has been already explained in the previous video. In the present video, we will be focusing in the use of registers and in how the registers are managed within the computer. This is the trial subtraction, and this is the restoring step when the subtraction is negative. To implement this flow diagram, the computer uses 4 registers and a counter: dividend, divisor, quotient, reminder, and the counter. The final result registers are built up successively by updating their value with the progress of the operation. Updating, updating, and updating. So, they are not separate registers. The final quotient result is shown in the window of the same quotient register, and the reminder result is shown in the last calculated reminder. Regarding the number of bits capacity required in the computer registers, if you are dividing two n-bit numbers, dividend and divisor, the result is an n-bit quotient and potentially an n-bit reminder. So, the final result uses 2 times n bits. Consequently, a restoring division in principle needs n bits for the dividend, n bits for the divisor, n bits for the quotient, and n bits for the reminder. So, a total of 4 times n bits. But in practice, you need only a total of 3 times n bits, because the quotient register is given a double use. Initially stores the dividend and then progressively is substituted by the bits of the quotient. Here I have converted the previous flow diagram into a circuit block diagram showing the use of registers and how they are managed by the computer. This is the divisor register with the signed digit in front. Here it is converted in 2's complement in case of subtraction. This is the quotient register, but as I said, initially the quotient register is given a double use. Initially stores the dividend and then progressively is substituted by the bits of the quotient. This is the A register, also known as the accumulator register. This is the other, as you see, includes n+1 bits to account for the sign bit. It is used to add the content of the divisor register and the A register. This is the control unit that controls the adding, subtracting and shifting. The control unit sends the shift left signals to the registers A and Q. During the process, the value of the register changes according to the progress of the operations. And at the end of the process, the actual values of the registers Q and A show the final quotient and the final remainder. Initially, at the start of the operations, the A register is all set to 0. Note that when we have to go for subtraction, the 2's complement converter is activated by the control unit. Then the 2's complement of the divisor is added to the A value. Now, when doing a left shift, the bits of the A are going to the left, and the space of A, which becomes vacant, is filled with the bits of Q. So, everything is going one step to the left, one step to the left. Correspondingly, the value of Q0 is left vacant, and it is the control unit who decides how to fill it, depending on the value of A. So, if A is 1, Q0 is set to 0, and if A is 0, Q0 is set to 1. So, this is the flow diagram converted into a block diagram showing the hardware needed to implement the restoring binary division method. Let's now work through an example of a division to see how the registers are managed by the computer. Our dividend D is 1011, which is 11 in decimal. Our divisor is 0011, which is 3 in decimal. We are working with 4 bits, so the process will take 4 cycles. At the beginning, the accumulator A is initialized to 0, and the quotient register Q is loaded with the dividend, so it starts as 1011. Let's see the first cycle. In the first cycle, we shift to the left the contents of A and Q. Then we subtract the divisor 0011 from A, which is equivalent to adding the 2's complement, which is 11101. The result in A is negative. Since it's negative, the quotient bit is 0. And according to the flow diagram, we have to restore A to its previous value. Cycle 2. In the second cycle, again, we shift A and Q to the left, and then we subtract the divisor from A, which is equivalent to add the 2's complement, 11101. This time again, the result is negative. Since it's negative, the quotient bit is set to 0, and we restore A to its previous value. Let's see the third cycle. In the third cycle, we shift left again, we subtract the divisor, and we check the result. The result is positive this time, so we keep it. That means the new quotient bit is 1. In the fourth and final cycle, after shifting left and subtracting, the result is also positive, so we keep it. The new quotient bit is 1. After all 4 cycles, the final result of the quotient is shown in the Q register, which is 0011. That means 3 in decimal. And the final remainder is shown in the final value of A, which is 0010. That means 2 in decimal. So the division is correct. Remember, each cycle of the algorithm follows the same pattern. First, shift the accumulator and the quotient to the left. Second, subtract the divisor from the accumulator. Third, if the result is positive, we keep it and set the new quotient bit to 1. But if the result is negative, we restore the accumulator to its previous value and set the new quotient bit to 0. And we repeat this for n cycles, where n is the number of bits. If you have difficulties in following these explanations, please keep at view a copy of the flow diagram and a copy of the block diagram to help you following the steps. In summary, in the present video, starting from the flow diagram, we explain how to convert the flow diagram into the block diagram of the restoring division circuit and how to perform the handling of the associated computer registers. To illustrate these explanations, we presented an example of how the division operation is performed within the computer and how the cycles of operations are implemented along the restoring process. That is all for today. Thank you very much for your attention. Have a nice day. If you like this video, please hit the like button and subscribe for more videos. Thank you. In the next video, we will further explain how to implement the non-restoring division algorithm.